Good day, doctor. Today we are going to present our study which entitled Static Analysis of Lower Back Loading During a Barbell Lifting. We are from Group B and I'm TEOH and my group mates are CHUAH, Chloe Teh Kai-yin and Jing. Now I'm going to introduce about lifting objects. Lifting objects is a common daily activity that involves significant forces acting on the human body, particularly the lower back. Improper lifting posture may lead to excessive bending moment and stress, increasing the risk of injury. In this study, a simplified physical model is used to analyze the effect of lifting posture on a bending moment, stress, and strain experienced by the lower back during a barbell lifting task. Then, how about our problem statement? Our problem statement is, during lifting, the position of the upper body and the angle of the back affect the distance between the load and the lower back, which directly influences the bending moment and stress. However, an improper posture may unknowingly increase these internal loads. A simple static analysis is required to study how posture angle affects the forces and bending stress acting on the lower back. In our study, we have used a physical model to draw a free body diagram and do calculations. We use human to represent a movable action figure, whereas the barbell represents as a point load. We do 2D analysis and the lower back is modeled as a fixed support. There are a few assumptions that we made in our study. First of all, the lifting motion is assumed to be static and the analysis is conducted in 2 dimensions. Next, the back is modeled as a uniform beam and the barbell is modeled as a point load. The lower back is assumed to undergo pure bending and all the effects of muscles, joints, and dynamic motion are neglected. We assume the value of parameters in our study and also the calculation. First, the mass of the barbell is equal to 10 kg and the weight of the barbell is equal to 98 Newton. Secondly, the upper body mass is equal to 24 kg and the weight of it is equal to 235 Newton. The distance to the barbell is equal to 0.5 meter and the distance to the upper body center of mass is equal to 0.3 meter. The dorsal angles analyzed in our study case is 30 degree, 45 degree, and also 60 degree. How do we obtain weights from masses? The mass of barbell is equal to 10 kg. We can calculate the value of it from equation W equal to mg, where m is mass and g is gravitational acceleration. We assume that g is equal to 9.8 in our calculation. Thus, we get the weight result of 98 Newton by using 10 times 9.8. Same goes to body weight. We obtain result of 235 Newton by using 24 kilograms times 9.8 in this case.
For this part, I will explain the free body diagram and force analysis of the weightlifting system. In this study, the human body is simplified into a mechanical system, focusing only on the forces acting during weightlifting under static conditions. In this free body diagram, we consider several forces. First, WB represents the weight of the barbell, which acts vertically downward due to gravity. Next, WU represents the weight of the upper body, which also acts vertically downward. At the lower back joint, reaction forces are present. Ry is a vertical reaction force that balances the downward loads. And most importantly, F, the lifting force. To analyze the system under static conditions, force equilibrium is applied. This means the sum of all forces acting on the system must be zero. We analyze equilibrium in 2 directions, vertical and horizontal. For vertical force equilibrium, we have F, the lifting force, plus the vertical reaction force, minus the barbell weight and also the upper body weight that acts vertically downwards equals to 0. As for horizontal force equilibrium, our horizontal reaction force equals to 0. It is important to note that all forces act vertically due to gravity, and the torso angle affects the bending moment through the perpendicular distance. It means that the torso angle will not affect our force equilibrium. Next, the bending moment analysis is carried out to evaluate the loading on the lower back joint. Although the forces act vertically, bending occurs because the torso is inclined at the angle to the floor. We use the moment equilibrium. Total moment equals to 0. So the bending moment equation is m equals the barbell weight times the distance to the barbell times sine theta plus the upper body weight and the distance to upper body center of mass times sine theta. This table shows the results of our manual calculations of bending moment due to different torso angles. At 30 degrees, the bending moment is the lowest. As the torso angle increases to 45 degrees and 60 degrees, the bending moment increases significantly. This is because a larger torso angle increases the perpendicular distance between the force and the lower back joint. In summary, the bending moment acting on the lower back joint increases significantly as the torso angle increases. This analysis demonstrates that larger forward bending angles during weightlifting generate higher mechanical loading on the lower back, which may increase stress and strain in the spinal region. Therefore, maintaining a smaller torso angle can reduce bending moment and lower the risk of injury.
Hi everyone, my name is Yixing. Now I will be explaining on the stress and strain analysis of the lower back during the lifting process. Due to the bending posture, the lower back experiences a bending moment caused by the weight of the upper body and the barbell. Using bending theory, we can evaluate the resulting stress and strain acting on the lower back. For simplicity, the lower back is modeled as a uniform beam subjected to pure bending as shown in this figure. Shear force and torsion are neglected to keep the analysis suitable for basic static conditions. Under pure bending, the maximum stress occurs at the outer surface, while the stress at the neutral axis is 0. The lower back is assumed to have a circular cross-section, and the radius of the circular cross-section is taken as 0.05 meters. And this is also the distance from the neutral axis to the outer surface. These assumptions allow us to calculate the bending stress using standard beam theory. The second moment of area is calculated using this equation for a solid circular section. By substituting the radius value, the second moment of area is equal to 4.91 times 10 to the power of 6 meter to the power of 4. This value represents the resistance of the lower back to bending. The bending stress is calculated using the flexure formula shown, using the bending moment obtained earlier for the 45-degree posture, which is 84.5 Newton meters. The bending stress acting on the lower back is calculated as approximately 0.86 megapascal. The strain in the lower back is calculated using Hooke's law, assuming the Young's modulus of the lower back tissue is 1 times 10 to the power of 9 Pascal, and then resulting strain is calculated as 8.6 times 10 to the power of minus 4.
Torsion occurs when lifting isn't symmetrical. It causes twisting of lower back and adds speed to spread. Although it is secondary to bending, torsion can still increase mechanical loading. Elastic torsion theory is used to analyze this effect. The torsion moment is calculated using T equals F multiplied R. Here, torsion comes from slight asymmetry or trunk rotation. When F equals 800 Newton and R equal to 0.05 meter, the torsional moment is 40 Newton meter. Torsional shear J is calculated using T equal to T multiplied R divided by J. The lower back is modeled as a solid circular section with a radius of 0.06 meters. Using a torsional moment of 40 Newton meter, the resulting shear stress is 0.118 MPa. From the result, torsional stress is relatively small compared to bonding stress. This shows that bonding is the dominant mechanical load on the lower back during lifting. However, maintaining a symmetrical posture is still important to minimize torsional effects and reduce injury risk.
From this comparison, we can see that as the torsion angle increases, the bending moment, stress, and strain also increase. A smaller bending angle results in lower mechanical loading on the lower back, which indicates that maintaining a moderate posture during lifting can help reduce the risk of getting injured.
Different torsional angle creates different load on the lower back. At 30 degrees, the strain is low, but the pressure is not particled. At 45 degrees, the load is moderate and the pressure is stable. At 60 degrees, the strain is high and the possibility of injury increase. So torsional angle between 30 to 45 degrees is best. This photo shows incorrect and correct lifting posture. In the wrong posture, the back is bent and the load is far from the body. This increases the moment out and the bonding moment on the lower back. In the correct posture, the back is straight and the neck are bent. Keeping the load close to the body reduces the movement out. This lowers the stress on the lower back and reduces injury risk. There are some limitations in this study. Firstly, a simplified mechanical model is used. Secondly, muscle forces and dynamic effects during lifting were not considered. Finally, the analysis is limited to static conditions and may not fully represent real lifting motion. In final conclusion, the bonding moment acting on the lower back increases as the torso angle increases. Proper lifting posture plays an important role in reducing stress and strain on the lower back. By keeping the back straight, bending the neck, and holding the load close to the body, mechanical loading can be reduced. Over a moderate torso angle between 30 to 45 degrees is recommended as the safest lifting posture.